My name is Kainton, the Tech Pro, and today we are going to be talking about yet another data structure for programmers, and today we are going to be talking about Bloom filter. I know something about you, that you know about hashing, you also know about caching, but that is cache memory. But one thing you don't know, I can be 80% sure that you don't know about Bloom filters. So the probability that you know about Bloom filters is about 0.2. And the probability that you don't know what Bloom filter is 0.8. That I can tell you. So, but this is the principle or the technology behind the working of cache memory, right? So how does it work? First, let's just take some theoretical background on Bloom filters. A Bloom filter is a data structure which is probabilistic in nature and is invented by a scientist called Howard Burton Bloom. So that is where the name came from. Bloom, Howard Bloom is a guy that discovered or invented this Bloom filter. Now, a Bloom filter allows false positive but does not allow false negative. So there will never ever be false negative in Bloom filter. Now, I said that Bloom filter has to do with cache memory. So how does a cache memory is? Cache memory actually, let's say something like this. This is a cache memory, and data is stored into cache memory. Now, the data stored into cache memory is frequently used data. So let's take, for instance, you always search for your girlfriend's name or your boyfriend's name in some social network profile. The possibility is that that data will be stored in a Bloom filter, and then next time you search for it, you can get it very easily with very good performance. So let's take, for instance, you search for a name Kate. So when you search for it the first time, it doesn't store it in cache memory. If you search for it the second time, depending on the design, it could be stored in cache memory. If you search for it the third time, depending on the design too, it can be stored in cache memory. So it depends on how the memory is designed. And let's now get to the fact, the aspect of the underlying principle behind this cache memory. So let's take, for instance, we have Kate. Okay, so the first time you are going to search for Kate, the system is going to look into the filter. Meanwhile, a Bloom filter is implemented as a binary array, so an array of binary numbers of zeros and ones. So this array of zeros and ones, of course, have index or has indices. So in this case, I've labeled the indices here 0, 1, 2, 3, 4, 5, 6, 7, 8. So the string Kate, you now search for it in Facebook or Google or whatever, wherever you search for it. What is going to happen is that the system is going to come to the Bloom filter and check if, let's get it right. Let's establish some things. We have M. M is number of slots. Then we have N, string length. And we have K. K now is number of hash functions. So these are the components that we have that make up a Bloom filter. So M is the number of slots. In this case, we have 12 slots because we are going from 0 to 11. N is the length of the string we are going to search. And K is the number of hash functions. So let's take, for instance, we are searching for Kate. So what is going to happen? Is going to pass it through H1. It is going to pass K into H1, okay? So assuming it hashes into, let's say, position 3. So what is going to happen? The Bloom filter is going to come to position 3 and place 1 in there. Every other thing is going to remain 0. The next thing it's going to do is going to check H1 of A. Alright, H1 of A, yeah. And it's going to give us position 6. So we go there and place 1. Take the next one, H1 of T let's say it gives us position 10, and we place 1 in there, and then H1 of E gives us position 0, and we place 1 in there, right? So in this case, let's assume that our number of hash functions is 1, okay? So the next time somebody goes to type Kate, if you go to type Kate and search for it, it's going to go to recalculate these hash functions. Of course, these hash functions are deterministic, meaning that if you pass the same item or the same character into it, it's going to give you the same thing. So when we pass, it passes K into the hash function H1. It finds 3. It checks, is there 1? Yes, it's 1. It checks A. Position 6, is there 1 there? Yes, it checks. Position 10, it checks. So it's going to recalculate the hash functions all over again and check if it's set to 1. If they are set to 1, then it will recognize that this function, this name or this string has actually been searched. But if eventually it finds 0, if eventually it finds 0 in any of these positions, then it will know that that name or that string has not been searched, right? And it's going to then set it to 1 and then assume it's not been searched before. However, if it finds everything to be 1, it's going to assume that it has been searched. The problem is, let's take for instance, you search for another string, ATE. Let's say ATE, that is 8. So this string has not been searched, but now when it goes to calculate H1 of A, it gives 6, checks is 1. It calculates HT of H1 of T, it finds 1. It calculates HE of H1 of E, it gives 0. So it's going to be 1, 1, 1 in these positions, and it's going to think that 8 has been searched. But actually it has not been searched, and that is when we have an error of false positive. Okay, so that is where false positive occurs. But whenever there is 0 in any of the slots, it guarantees that that string has not been searched. So there will never be a false positive. It will never report that a string has not been searched when it has been searched. So no, anytime a 0 is found anywhere in the slots that it hashes to, is guaranteed that that string has not been searched. The reason is because if it has been searched, it will be set to 1. Alright, let's now go to do a little analysis of exactly how a Bloom filter works. Now we are trying to calculate the probability of false negative, and we are saying that, let's say, the probability that an item is set to 1, right, is given by 1 over m, right? Now the probability that an item is not set to 1 is given by 1, so let's call this P of 1. So P of, let's say, not 1 is now equal to 1 minus 1 over m. So there is a probability that a bit is not set to 1. Alright, so now if we have k hash functions, then this probability will be 1 minus 1 over m to the power of k. Okay, now if we take it for n strings, then we have 1 minus 1 over m to the power of k times n. Alright, so this is the probability that a bit is not set to 1, that a bit is set to 0. Now the probability that a bit is set to 1 when it's actually not supposed to be set to 1. Now this is a bit confusing, but I don't have any option, I have to write it. So that probability probability of false positive equals, so this time we are subtracting 1 minus 1 over m kn, sorry, not kn. So this is now the probability that a bit is set to 1 when it's actually should be 0. Okay, so if we now take it for the k number of hash functions, and that is going to give us 1 minus 1 over m kn. I don't know why I keep making this mistake. Kn all to the power of k. So this is the probability of false negative or false positive, and hopefully this probability has to be very, very small. Now consider what happens when the value of m, that is the value of m, is large. M tends to infinity. M becomes very big. That's, you have so many slots in your Bloom filter. What is going to happen is that this 1 over m is going to vanish. So at that point it's going to be 0. So what you have, 1 minus 1, 0. And then this probability, let's just call it PR, is equal to 0 or tends to 0. So as the number of slots in your Bloom filter increases, the probability of false positive reduces drastically. So to improve the quality of the Bloom filter, it means that we need to have more slots in the Bloom filter or in the binary array. So if m tends to 1, m size of the number of slots or the cache memory or the Bloom filter is very small, the number of slots, then what is going to happen is that this quantity here is going to tend to 0, is going to tend to 1. So what we have is 1 minus 1, 1. So we have 1 minus 1, 0. So we have 1 minus 0 to power k to power kn to power k is going to be 0. So the probability tends to 1. So this is how Bloom filter works. I'm going to stop here. I hope this has been informative for you. If so, subscribe to my channel by clicking on the subscribe button below this video. In subsequent lessons, I'll be bringing you more theories, and I want to mention that you should not be tired of learning some of these basic things. I know they are boring, but as a computer engineer, computer scientist, programmer, or IT professional in any way, you need to have some ideas of how things work in the background. That is what actually gives you an edge over others who are doing the same thing. So I'd like to thank you for viewing. If this has been informative, leave me a comment to know. If there is some particular data structure you want me to discuss, also let me know in the comment box below.